In today's video, we're going to look at the second half of rational functions. So in our previous video, we looked at the definition of a rational function, and we started looking at these asymptotes, the horizontal and vertical asymptotes, and how we find those for a particular function. We're going to carry on with that in today's video and look at oblique asymptotes and see when those may arise. We already know when those horizontal asymptotes may arise, but let's see when those oblique asymptotes may arise, and then we'll look at holes in these graphs of the function and when those may arise, and then we'll look at actually graphing one of these and the steps that you need to go through in order to graph one. So first of all, let's look at those oblique asymptotes. So like we said in the last video, there are three different cases for horizontal asymptotes. Okay? The case where there was no horizontal asymptote was when the degree of the numerator was greater than the degree of the denominator. So you had a higher power of x in your numerator than your denominator. Okay? An oblique asymptote occurs when the degree of the numerator is exactly 1 greater than the degree of the denominator. So if I have a rational function where I've got a polynomial over a polynomial, if the degree of p of x is exactly 1 more than the degree of q of x, then f of x has an oblique asymptote. So obviously, if a particular rational function has a horizontal asymptote, it can't possibly have an oblique asymptote because of the properties that we must have in terms of the degrees of the polynomials. And if a particular rational function has an oblique asymptote, it won't have a horizontal asymptote. So how do we find the equation for an oblique asymptote? Well, you have to do some polynomial division to do this. You're just going to do p of x divided by q of x using polynomial division. Then whatever you get on the top when we do this polynomial division, I'll show you this in a second, whatever we get on the top when you do this division, that is going to be your oblique asymptote. Any remainder we're just going to leave behind and not worry about it. But it's the main terms that you get when you do this division, and we're going to ignore any remainder. Okay, so let's do a quick example of this to show finding an oblique asymptote. So let's say we had f of x is equal to 2x cubed minus 5x squared plus 2 divided by x squared minus 3. Okay, again, the degree of our numerator is 3, the degree of the denominator is 2. So the degree of the numerator is exactly 1 more than the degree of the denominator, so we know we can go ahead and do this polynomial division and find the oblique asymptote. If you have a difference of more than 1, so for example here if we had that the degree of the numerator was 4 and the denominator was 2, then there is no horizontal asymptote and no oblique asymptote. This is only when you have the difference of 1. Okay, so we've got to go ahead and do that polynomial division. Wherever you have a particular x term or x squared or whatever it may be in your polynomial that does not have a coefficient, so it has a coefficient of 0, so it doesn't actually appear, you'll see that there is no x term here. We just put plus 0x, especially when we do this polynomial division. Okay. So now we go ahead and do this division. So I look at how many times x squared goes into 2x cubed. That would be 2x, because 2x multiplied by x squared gives me 2x cubed. Then I multiply my whole outside polynomial by that 2x. So that gives me 2x cubed plus 0x squared minus 6x. I then do a subtraction, so I get no x cubed term, and I get negative 5x squared minus 0x squared, so that's still negative 5x squared. Then 0x minus negative 6x is going to give me positive 6x, and then 2 minus 0, I still end up with 2. I do the same thing again. What do I need to multiply x squared by to get to negative 5x squared? And that would be negative 5. And then I multiply the whole polynomial by negative 5. So it would be negative 5x squared plus 0x plus 15. Do a subtraction. That would leave you with 6x minus 13. Now, there is no number that doesn't include a fraction here that I can multiply x squared by to get to 6x. That would involve some division. So I know that I'm done. Whenever your degree of a polynomial down here is less than the degree of the polynomial that you are dividing by, you know that you're done. And then whatever you are left with at the top, so in this case 2x minus 5, that is the equation of your oblique asymptote. So the oblique asymptote is just the line y is equal to 2x plus 5. Okay, so of course that is going to be a diagonal line, hence an oblique asymptote. It is not going to be horizontal. We'll do one more example of this. This time I'm going to have f of x is equal to 4x cubed plus 2x squared plus 5x plus 1 divided by x squared minus 3x plus 2. So again we have this rational function, and in order to find the oblique asymptote, I don't have any missing terms this time. I have x cubed, x squared, x's and constants. So I know that I can just go ahead and write it as is. What do I have to multiply x squared by to get to 4x cubed? That would be 4x. Then I multiply my whole polynomial through by 4x. I do a subtraction, and that would leave me with 14x squared minus 3x. And then I have to see what I need to multiply x squared by to get to 14x squared. That would be 14, so I put plus 14. And then I multiply my whole polynomial through by that 14. Okay, subtract. And at this point again, my polynomial down here now has a degree that is less than the degree of the polynomial that I am dividing by, so I stop. And whatever is left at the top is the equation of my oblique asymptote. Now we need to look at holes in the graph of a rational function. If you remember before, when we were trying to find the equation of the vertical asymptotes, we put our particular rational function into factored form so that both the numerator and denominator were factored. We then simplified, so we got rid of any terms that appeared on both the numerator and the denominator. They got cancelled out. And then whatever was left on our denominator, we set equal to 0, and that gave us the equation of the vertical asymptotes. Well, I said that we would come back to those terms that we ended up cancelling out. If you actually take those terms and set them equal to 0, those are going to be the holes in the graph. Reason being, we know that with our domain, for the domain we set our whole denominator equal to 0. Okay, and wherever the x values are that give us the 0 on the denominator, we know that those x values are not in our domain, so our function is not defined at those x values. So therefore, if they're not going to be a vertical asymptote, they have to be a hole in the graph where this function is not defined. Okay, so let's do an example of this. I have f of x is equal to x plus 6 over x squared plus 11x plus 30. Okay. If I go ahead and factor this, that's always the first step, go ahead and factor it. I get x plus 6, x plus 5. Okay. So I already know that the domain of my function is all real numbers, but we're going to exclude anywhere that gives me a denominator of 0. So that would be when x is negative 6 or x is negative 5. Okay, so I know already that my function is not defined when x is negative 6 and when x is negative 5. Okay. My next step when I do this, when I did this before, to find the vertical asymptote, I simplified my function to give me that. So I know that I have a vertical asymptote wherever the denominator is 0 in simplified form, which means that my vertical asymptote is at x is equal to negative 5. Okay. So what about this negative 6 value? Well, we did this cancellation here, where I had x plus 6 on the numerator and x plus 6 on the denominator. Okay, my function is still not defined at x is equal to negative 6. So when you had this factored form, any term that appears on both the top and the bottom, I'm going to set equal to 0 and solve it. And at that particular x value, there is a hole. Okay. If I then take that x value and plug it into my simplified form, that will give me the y coordinate of that hole. So I know that I've got a hole at x is equal to negative 6, but what is actually the coordinate of that hole? Okay. Well, if I plugged x is equal to negative 6 into my whole equation here, I know I'm going to end up with some undefined value because my denominator is still going to equal 0. So to find the y coordinate at that hole where this function is not defined, I'm going to plug x is equal to negative 6 into here. That will give me y is equal to negative 1. So I know that I have a hole at negative 6, negative 1. So all I do when I draw my graph, and we'll do this in a second, you figure out where your vertical, horizontal or oblique asymptotes are. Once you've done that, if there is any term that you cancelled out, set that term equal to 0, figure out what the x coordinate is for that hole, figure out its y coordinate by plugging that x coordinate into our simplified form of the function, and then once you've drawn out your graph, at that one coordinate, you're just going to put an empty circle. So you're not going to put a line. It may be in the middle of the line. You're just going to put an empty open circle. Okay. Now, let's go ahead and talk about actually graphing these. So putting all of these pieces together. How do we graph a rational function? I'm going to go through step by step how you're going to do this, and then we're going to do an example. So this is going to be a step by step of how to graph a rational function. Okay. Step 1 is to factor your numerator and denominator. So you're going to write f of x is equal to p of x over q of x in factored form. A good thing to do at this point is also, once you've factored the numerator and the denominator, find the domain of the function. Because you know at those points where f of x is undefined, you're either going to have a vertical asymptote or you're going to have a hole. So it's kind of good just to see what your domain is before you go ahead and do those next things. Next thing you're going to do is to find the common terms in the numerator and denominator. Okay, so that's what we did in order to find the holes. So find the common terms in the numerator and denominator. Okay. And use those to find the holes in the function. Then cancel them out and find the simplified form, because our next step is going to be finding the vertical asymptotes. So cancel these common terms out. And write f of x in simplified form. Okay. Then your next step is going to be to use that simplified form of f of x and set its denominator equal to 0, and that will give you the x values for which you have a vertical asymptote. So for the simplified f of x, set the denominator equal to 0, to find the vertical asymptotes. Okay. Then what you're going to do for those vertical asymptotes, take your xy coordinate plane, quickly sketch out an xy coordinate plane and dot out the line x is equal to whatever it might be, where you have a vertical asymptote. Okay. The next step is dealing with any horizontal asymptotes. So you're going to compare the degree of the numerator to the degree of the denominator for our original f of x. So we're not worrying about any simplified forms or anything like that. Go back to the original f of x. And compare the degrees of p of x and q of x. Then you're going to draw any of those horizontal asymptotes in with a dotted line again. Step 5, if we don't have any horizontal asymptotes, determine if there is an oblique asymptote. So if you have that P of x has degree 1 greater than Q of x, you know that there's an oblique asymptote. Okay, so find the equation of the oblique asymptote and dot that in if there is one. To make your sketch slightly more accurate, we are also going to find the x and y intercepts of our graph. So this is just done as normal. Take your original f of x, set x equal to 0 to find y intercepts, set y equal to 0 to find x intercepts. And the last thing to do before we actually draw this is to determine the end behaviour using that horizontal asymptote that you have. So look at what happens as x goes towards positive or negative infinity so that you can see what actually happens at the end behaviour of this graph. And then we can go ahead, put this all together and draw it. Okay. I'm going to do this via an example so you can actually see this in action. So I'm going to do the example of f of x is equal to x plus 5 times x minus 1 over x minus 6, x minus 1. I've already factored this just to kind of skip a step with this, but if this wasn't already factored, please make sure that you factor it first. First thing I would do again is find the domain, just because it helps us with the holes and the vertical asymptotes to make sure that we have accounted for all points where this function is not defined. So we can already see that the domain of this function, if I set my denominator equal to 0, my domain is all real numbers except for when x is 1 and when x is 6. Then if I were to simplify this function, I end up with x plus 5 over x minus 6. I have cancelled out the x minus 1s, telling me that if I set x minus 1 equal to 0, so x is equal to 1, at x is equal to 1, I have a hole. What's the y coordinate of it? I plug this into my simplified form, which would give me negative 6 over 5. So I have a hole at the point 1, negative 6 over 5. Okay. Again, using my simplified form, I can find my vertical asymptote. So my vertical asymptote is wherever my denominator is 0 in simplified form, meaning that my vertical asymptote is at x is equal to 6. So I'll come over here. If I were to quickly draw out an xy plane, I know that at x is equal to 6, I'm going to have that vertical asymptote. So 6 would be here. Okay. Now, coming back to what I had here, my horizontal asymptote, okay, I have the same degree of polynomial on my numerator and denominator, which tells me that my horizontal asymptote is at the ratio of my leading terms. What's my leading term of my numerator? Well, my leading term would be x squared. So my leading coefficient is just 1. Same on the bottom. My leading term is x squared. My leading coefficient is just the coefficient of that, which is again 1. So my horizontal asymptote is at y is equal to 1. So again, I come back to my xy plane, and at y is equal to 1, I'm just going to dot in my line. The next thing that I do is I find my x and y intercepts. So my x-intercept is found by setting y equal to 0. When you do this x-intercept and you set y equal to 0, make sure that your function is in simplified form to do this, okay? Get rid of any terms that occur on both the numerator and denominator and just use this simplified form to find any x-intercepts. So the x-intercept is where y is equal to 0, which means that I am setting my numerator equal to 0, okay? Which in simplified form means that my only x-intercept is where x is negative 5, which would mean that my x-intercept is negative 5, 0. Again, you may end up with more than one, even in simplified form. If you still had a quadratic in simplified form, then you know that you're going to end up probably with more than 1, 0. Okay, so just kind of be aware of that. With x-intercepts, make sure that you are doing this in simplified form. Okay. For the y-intercept, you should find that things actually cancel themselves out even if you don't use simplified form. It can be easier to do this for simplified form, but you do not need to do that. So for y-intercept, you set x equal to 0. And if you do that with our function, you should find that your y-intercept is 0 and negative 5 over 6. The last thing we need to do is to look at the end behaviour. Okay, so what happens is x goes towards infinity and as x goes towards negative infinity. Okay, well, this comes back to our horizontal asymptote. We actually have a horizontal asymptote in this case. So we know what happens as x goes towards positive and negative infinity. We talked about this with horizontal asymptotes. If one of these exists, then you know that as x goes towards both positive and negative infinity, it must approach this value of y. Okay, so when we come back to here, we know that as x goes towards positive infinity, it has to approach this line. And as x goes towards negative infinity, again, you know it has to approach this line. Okay. So now that I know what the end behaviour of my graph is, I'm going to quickly plot my x and y intercepts, and that should help us with the shape of this graph. Okay, so we said that our y-intercepts, or where we intercept the y-axis, is at 0, negative 5 over 6, which you can say is roughly around there. And then our x-intercept was at negative 5, 0, which we'll say is around there. So I know that because I've got to approach that line of y is equal to 1, the shape of my graph on this side will be something like this. So I must be the opposite on the other side of my graph. Again, in both directions, as x goes towards infinity and as x goes towards negative infinity, I'm approaching that horizontal asymptote. The last thing that I need to do is to actually draw in that hole. So we said that there was a hole that existed at 1, negative 6 over 5. So at 1, negative 6 over 5, that would be, I'd say, roughly here. So if I take that out, I'm just going to draw an open circle at that one point, and then the line carries on either side, because I know that the function is not defined at that one point, so I just draw it as an open circle and the line carries on either side. So this is how I would recommend you do any of these problems. You go through this systematically, finding your asymptotes, finding the holes, finding the x and y intercepts. Plot these on the graph, look at what your end behaviour looks like, so what happens as x approaches positive and negative infinity, and then using the x and y intercepts you can find out pretty much what the shape of the graph is and which way it's actually going to approach that line, and then you can plot it.